Okay, so it seems that I get slightly better questions out of the class if I go through a printout and we talk about what it all means. So what I wanted to do is to come down here and talk about the program code that we have for the one predictor model and to tie up any questions we might have here. So the data set that we're looking at is this data set, and we did a little bit of a correction on this in terms of the range, and we're looking at the Mplus program. So if we come into this program code, this is what it looks like, and I've sent this out to you. So, here's our file that we're analyzing. Here's a little bit of code that I put in to recode values that are bigger than 17 to be 17 because of the nonlinearity we saw from the lowest regression. And here's the statement that says the single predictor variable is a categorical one. And because this isn't, and in the middle here, as I mentioned in the handout, it's sometimes useful to center the predictor variable, the continuous variable, to a mean of 0, and that's because that makes the intercept correspond to some value that is close to the centroid or close to what the average proportion in my sample looks like. And if I would want to, I can run MLR with a link logit function. This is not the default behavior, but given that the default behavior is WLSMV, but given this particular sample, I'm going to get roughly the same answers out. And in here is my statement that talks about the regression predictor. So this is predicting the categorical variable from the continuous variable. And I would like to have the sample statistics. I want to take a look at the standardized coefficients. And this will give me the plot of extra output plots that we can talk about. And I want to take the particular plot things I'm interested in looking at is the log likelihood, the influence diagnostic, and Cook's D. So down here, this is all of the information about what we are doing. I can answer any questions you might have on it, but generally speaking, I don't look at this part of the printout. Down here, here's our categorical variable, and this is the data. This is not from your model. This is saying that in the data set, there's 618 students who didn't do 5 or more drinks in a sitting, and 1,351 who did, and these are the proportions. Here's the sample statistics for the continuous variable because I centered it. I've got a 0 here. And this is the variance covariance matrix of the predictors. So this is saying the variance of my continuous variable is 12. And that would correspond to a correlation coefficient that's just got one variable in it with the number 1. And down here are the summary statistics, the mean, the variance 12.14, the skewness and kurtosis values. So this is the continuous variable is negatively skewed. The minimum and the maximum values, and the percent of people in the population with the minimum and maximum values. And here are the percentile points, the 20th and 60th, 40th and 80th, and the median number is 0.6. So it's fairly skewed, as you can tell from the negatively skewed value, and also the fact that the mean of 0 is pretty far close, pretty far away from the median of 0.6. Downstairs, we have our fit functions here. So the log likelihood you would report, generally speaking, the BIC has been a statistic that we've talked about that we can report. And in here we have the prediction of the dichotomous dependent variable from the continuous, and this is my unstandardized value. And here's my threshold. Downstairs, we see the results in probability scale. So 0.314 and 0.686 are pretty close to the values that we had upstairs in our raw data values. And this logistic regression is this divided by, sorry, we'll get to that logistic odds ratio in just a minute because that's the continuous variable. It sometimes helps to sit down and play with the data from an output in a spreadsheet format. And so that's what I've done here. This is just the same printout as you saw before. So here's the threshold. Now this is a logit function. This is the threshold we just saw in the printout. And if I take this number and divide by 1 plus e to that number, that gives me 70. And that number is pretty, and that's going to be the number, the relative proportion of the number of people in category 2. And in this particular value, that's pretty darn close to the 686 that I have. And you might wonder, well, why is it the case that I don't have that number exactly matching up? And as I explained in the chapter, that's because the parameter value that I have in here is a value that's arrived at going over each of the individual observations. But this is just to show you in Excel how this is getting the number and what that particular threshold means. And downstairs, I have here the standardized values. So if I standardize the latent response variable, that's going to give me this value. And so that's pretending if I have a latent response variable 1 and a manifest variable 1. So you can interpret this thing as a standardized regression weight, more or less. Now, the nice thing about these is if I come upstairs and I take my parameter value and I say, take the exponent of that, that's going to give me the odds ratio. So downstairs you see 1.285. That's the odds of diagnosing divided by the odds of not diagnosing, or in this case, drinking 5 or more drinks in a sitting versus not drinking 5 or more drinks in a sitting. That's e to this number is 1.28403. So the more reasons you have for drinking, the more likely your odds of increasing in the odds that you will drink 5 or more drinks is 1.2. And I can do the same thing downstairs for the standardized coefficient. Associated with that. So e to that number is 1.5432 if it's standardized. So the reason that that's larger than the other one is, remember, this continuous variable in the standardized solution has a variance of 1. So a 1 point increase in the standardized value is going to be different than a 1 point increase in the unstandardized value. And downstairs, I have here an estimate of the R-square for the model. That is then taking this 0.434 times 1 for the variance period times 434 gives me 1.88. So that's walking ourselves through what this code is doing and what these numbers actually mean. And that ties us into what we're looking at in the code here. So the one we had in here was the MLR, the MLR with a logit length function. So, as I mentioned before, some of the nice things about Mplus is it will do some things that aren't readily available to you in other places. Remember, upstairs in this, I have put in a plot statement. So let's take a look at that. There's this little, button up here in the upper left-hand corner that accesses the plots. It's colored. That tells you there's something to look at. And you can have some things that are fairly banal, like histograms of the number of variables in zeros and ones. And that'll tell you the proportions of zeros and ones. Similarly, I can come upstairs and take a look at that distribution of the continuous variable. And here we see that it's negatively skewed. The reason that these boxes are all discrete is because we took the average of the individual, reasons for drinking scales. These were Likert format scales, so we don't have even spaces in here. And the scatter plots are the more interesting in this particular data set. So even though we have a conclusion, we have an analysis, we might want to take a look at whether we think there are influential observations present in the data. So I can look at influence and scatter plot that by the Cook's D. And here's my little plot. And we see from this that probably, there are, even though this is a rather large data set, we have some variables, some observations in here who are influential. And as I mentioned before, if you were doing this for an article, you would save the influence diagnostics to a data set and then reanalyze that and say, oh, by the way, we run this model and throw out the following folks with influence diagnostics. You can hover over these individual little plots, excuse me, and we should, after a short while, see an observation. So this is a person who did drink 5 or more drinks in a sitting and had an extremely low value on the reasons for drinking analysis. So, that particular person maybe is going, if you rerun the model without that, your resulting guesses about the log likelihood, what the regression weights are, is going to increase quite a bit. If we come back out here and look at this person in the upper right-hand corner, that's a person who's even more extremely saying, these enhancement is not a reason for drinking. So these influence diagnostics are looking like they're kind of counter or contra the model that you want to publish. But when you write it up, you would say, I did due diligence. I did a lowest regression to see if it looks like a straight line. I specified my model, and I looked at the influence diagnostics to see if my claims about the magnitude of the effect are unduly influenced by a few people. Yes, there seem to be some influential observations, but as a result, the analyses that I'm looking at here are probably underestimates. So is that working? And I hope I'm making good on the promise that basically to do dependent categorical verbs, you just need to put that material, that line in there. Hit the run button. The defaults will give you WLSMV, and you'll have answers out there. There's a few small wrinkles in this that we could talk about. You'll notice downstairs here, I commented out these following 2 lines. And this has to do with a slight wrinkle of a difference between Mplus and, say, Lavon or other packages that will do this type of thing. In Mplus, if you have a continuous variable and you're interested in knowing how that affects a dependent variable, that predictor variable is not formally in the model, because the only thing that you're estimating is the regression weight and its significance. So in order for you to bring that formally into the model, if you wanted your results to reflect the variance and the mean, you'll have to explicitly say that by uncommenting this line. And that's not going to affect influence diagnostics. It's not going to affect the fit. You'll get a slightly different BIC value out. But your model comparison statements should work just the same as before. So if we come back to that, that's what's going on. If we're doing a probit regression, it's the same thing. The printout's going to be the same, except your threshold is now going to be an approximate z-score. And that's going to give you, these particular sets of numbers. And I walk you through that here. We talked about that last time. So do you have any questions here about that? Going once, going twice, going three times? Okay. Before I wrote this chapter, I had made a handout to talk about categorical data. And the next topic that I want to take up is item response theory. And my objectives here are to help you see that all of item response theory is just another structural equation model. And the small wrinkle here is that it has a dependent categorical variable, just like what we've been talking about. Now, item response theory was born with a different set of institutions, a different set of people working on it. So they have slightly different notation. And they also talk about parameters when in judging how an item responds. They're just a little bit different. They're pretty straightforward though. So the first thing I want to do is to talk about some notation. There's some Greek notation, and the first little bits are going to be exactly what we've been talking about with your old Mplus for the notation of the factor model. It's modified Liswell notation. So a manifest variable is just the intercept associated with that model. It's the arrow from the unit vector pointed at a manifest variable. A factor mean is denoted with alpha. A factor variance with psi. That's one of two options you can use. And our factor variances are usually denoted with theta. So that's upstairs. This is all of our notation for continuous structural equation models. Now downstairs, we talk about categorical dependent variables, latent response variables. And there we talked about pi, the probability of being in a category, and tau, our threshold that cuts the latent response variable up into the categories that we have in our data. So far, so good. And we can talk about our latent response variable, and that has a mean, mu star, and that has a variance, sigma star. I don't really like the fact that they dropped the 2 upstairs in the superscript, because usually just looking at this, you'd think that means a standard deviation, but such is the notation. As I point out here. And there's this other little beast that we talked about last time called a scaling factor. Well, the scaling factor can be the variance. The variance can be expressed as 1 divided by the scaling factor squared. And the reason we're mucking around with the scaling factor is kind of a technical math thing. It's just is the case that it's easier to have the computer program search and minimize your latent response variable and your categorical dependent variable, thinking about this delta instead. And just the same way that is the way to get from a variance to delta is via this formula. So that covers regular old continuous variables, categorical dependent variables, and latent response variables. Now let's talk about some language for discrimination. And A is our value that we use to talk about discrimination. So we'll get to this in a minute and we'll see a picture that will make it a little clearer. But the discrimination is something that tells me how informative my variable is for discriminating between levels of my factor. And what I have in here is a restatement of what was in the chapter. When we're playing with latent response variables, we set a metric. Sometimes we want the whole variance of our latent response variable to be 1. Sometimes we want the error variance associated with the manifest variable to be 1. In terms of the factor part of the model, we assume that mu is 0. And we quite frequently assume that alpha, the factor mean, is 0 as well. This needn't be so for all of our models, but it's the default behavior. And when you're doing IRT models, this is pretty much what you think about. And this point are in bullet point forms, what's talked about in the chapter. If I've got variance to be 1, then my error variance is going to be this. And if I have theta and a scaling factor as well, the error variance is going to be this in terms of the scaling factor. So those are 2 ways to think about what our error variance is going to be. If we want to specify our model in terms of theta being constrained to 1 instead of the factor variance, we're going to get this formula out for the delta. And this is again a rehash from the chapter, but if I'm playing with delta, my error variance is going to be this. And if I'm playing with theta, my factor variance is going to be this. And these are the 2 ways that I can specify what I've got going on. If I want to have error variances correlated in the model, I need to say parameterization is theta. Writing the default of delta is okay if you don't have that, and you'll find that your programs are going to run a little bit better. They'll converge a little bit more often. They take fewer resources. And downstairs, we have 2 link functions. Well, in the latent response variable model, we talked about the probit and the logit link function. So now let's get into 2 things that talk about items. An item can be difficult if relatively few people actually answer the item correctly. An item can discriminate if it's going to have a steeper curve going on. So let me come over here and we'll just walk you through a printout that does an item response theory model. And it'll be a little bit easier to see what's going on. Excuse me, got to run this again. So, and I've sent this code out to you as well. It's an example from the Mplus manual. So here's our title, here's our data, and what we're looking at now are 20 dichotomous variables. And all 20 of these dichotomous variables are categorical. And I'm doing weighted least squares, MV, and I'm using delta parameterization. Right, so those are all kind of technical things. What I want you to hopefully happily notice down here is this is all the factor model is. Item response theory is saying I have a latent factor here, and that factor has as indicators 20, in this case, binary variables, and the factor variance is 1. And let's just, for the moment, walk through this printout and see if this generates any questions. Here's my 20 items, and here are the proportions of zeros and ones I have in the data. Here's my factor, my fit results. This is my chi-square. And as I mentioned last time, we can't take this chi-square and do chi-square differences on it. And Mplus now happily gives you a little warning and says, if you want to compare this, say maybe have a model where one item doesn't contribute to the factor and zero out a loading, or say there is more than one factor underlying the data, you'll need to use the diff test option. Here's the RMSEA, the TLI. All of these are our regular standard structural equation modeling fits. And downstairs, we have our loadings. So here's all of our factor loadings. And downstairs, here are all of our thresholds. Well, I'm using, as I say upstairs here, I'm using a logit link function. And where did we have that little bit of information? I'm sorry, we're doing a probit link function. It's normal. So these numbers can be thought of as z-scores. So a positive number here indicates that the threshold exists above the mean of 0. So that's telling you most people did not answer the question correctly, and a few people did. And similarly, I'm sorry, that's the loading. I meant to be down here at thresholds. A negative number is going to say fewer people failed the item and most people got the item correct. And here I have a positive number. That means the threshold is above 0. That means more people did not answer the question correctly than did. So this threshold can be thought of kind of sort of as a difficulty in terms of saying what proportion of people did or did not answer the question correctly. Let's take a look at some pictures because I think those are going to make things a little bit easier. And let's look at item characteristic curves for all of these things. Here we see a line graph of the relationship between the latent variable f and the probability of answering the question correctly. So in this picture, an item will be difficult if the line that I see here is going to be farther over to the right, because that will mean that even if I have a high value of whatever this latent variable is, the probability of answering that question correctly is low. An item that is easy is going to be more over here to the left. And that means like this item, for example, would be one that's kind of sort of easy because the probability of correctly answering it is a little bit higher than 0.2, even if you're have a score that's very low on this factor. So that's difficulty, left to right. Right being harder items, left being easier items. Discrimination has to do with the shape of this curve. So in this particular case, we have a bunch of items over here that seem to have this shape and another set of items over here that seem to have this shape. The slope of the lines are different. So this item slope is pretty much the same over all these values, and this one has kind of an ogive shape to it. So discrimination is the ability of this latent variable to correctly identify increases in the probability of successfully answering the question. So while you might think that difficulty is, one characteristic of items that we can certainly relate to, we've all taken tests that were really easy or really hard in life. The discrimination informs you of the ability of an item to discriminate between people at various levels of the latent variable. So if you want to design an instrument that will correctly differentiate between people at a given level, you'll want to go in and pick items that correctly diagnose or informative about probability of correctly answering your question at various levels. So these items, for example, here are maybe more useful if you're interested in discriminating between people at lower levels of the latent variable. these items over here are giving you the ability to discriminate between individuals at higher levels of this. So if you're designing a survey and it's your, the objective of your survey is perhaps to identify people who qualify for a gifted program, yes, you might like to have more difficult items than you otherwise would, but you also want to have items that will discriminate more at the higher end of this latent variable. Is that working? So what we see down here are discriminations. And, for example, this item 11, has a relatively steep discrimination. It'll tell you more at some level. It'll tell you who does and does not answer the item correctly. Downstairs, we have our difficulties. Well, these difficulties reflect the thresholds that we have in the probit model. They are values for indicating items that were easy and items that were harder. So let's just kind of, in terms of the picture, take a look at two items. Let's do an ICC for item 11 that had a high discrimination, and an ICC for item 14 that did not have a high discrimination. Here's item 11, and I said item 14. So, this item did not have a discrimination. It kind of tells you across all levels, well, people down here have a relatively low probability of answering things. People over here have about an 80% chance of answering the question. But if you're wanting to identify people, to discriminate between people at this level, slightly above the mean, this item does a better job of discriminating between people below this level and people above this level. Does that work? So just as before, here's the printout that we had, and I'll make it bigger so it's easier to see. Here's the proportions in our population. And here's our factor loadings. And here's our thresholds. And what I wanted to do here is just to apply the formula that you saw in the printout that will take, just copy and paste this so that you can see it. Is I'm taking the square root of delta and multiplying it by the factor loading, and this gives me, and divided by 1.7 for math reasons, that's going to give me the discrimination. And similarly downstairs, the formula that I have for the difficulty is to go upstairs and pull the factor loadings times the variance of the variable and divide that by the delta and the square root. So those are the formulas that will go to various parts of the printouts and pull those numbers and give you the numbers that you're seeing there. Okay. So this was the highest difficulty item. It's got the highest value there. So, that's kind of walking you through a printout, how item response theory works. And I walk through the equations for that and give you, the individual probabilities based on the thresholds and the loadings for getting these values. So inside of item response theory, there are these things called Rouch models. Rouch models are different than the two-parameter IRT model that you saw because they assume that all of the factor loadings are going to be the same. In other words, that there's a latent variable called f out there, and there are loadings on it, but the loadings are same across all items. So that means that the individual items cannot differ in terms of their discrimination. Rouch models are pretty easy. They're pretty easy to calculate, and they're generally more popular in areas of classroom assessment where you have a relatively small number of people. And the primary thing that you want to do is to identify items that will, identify people at higher and lower levels of the latent variable. And what I had done here is to take a little longitudinal data example. I took people at a data set where I had an assessment before they went to college and then across 8 semesters of college. And I said, did they or did they not drink 5 or more drinks in a sitting? The data here is a little bit different than that first one I showed you. And I fit a Rouch model to that. And as you can see here, this gives me the predicted proportions of people on the latent variable across the different waves that I have here. And the corresponding threshold in my loss model is this. The thresholds can vary across the individual items, although the loadings are the same. And the difficulty levels are this. So, what we're seeing here is this value at pre-college is when students are the least likely to be drinking 5 or more drinks in a sitting, and then they come to college and that number keeps going down and down. Right. Any questions on that?
Can we go back to the Mplus printout and the item characteristic curves for just a moment?
This one?
Oh, can we go to the Mplus printout?
Oh,
yeah. You might have closed.
I might have just closed the wrong one. Yes. So, a second.
I could probably ask.
No, that's fine. I'll get there. I'm in the. Okay. So when you wanted?
The item characteristic curves of the 2 items that you.
Yeah, sure.
Yeah, distinguished.
Okay. And I think it was 11, and what was the other one? Hold on a second. That was 11 and 19. Okay. Okay.
So I assume that there will be some items whose difficulty is kind of in the middle, and you don't see as much of a distinction as you do here in like item 11, where that looks very obvious to me. Like there's a discrimination between like two groups who get it right and get it wrong. But, and then item 19 also looks fairly obvious that there's not a distinction, but is there a way that you can tell when maybe it's not quite as clear as these two items?
Well, yeah, we can. What's kind of close? I mean, so 11 and say 17, they're going to have kind of the same shaped curve. They might differ in terms of their item characteristic curves, in terms of their difficulty. So just messing around here, let's go out and get 11 and 17. Okay, so those are two items that are performing, you know, almost identically. You know, in practice, even though their discrimination is the same, one item could be more difficult than the other. You know, so that, I guess it's important to say the name of the game here is you're trying to use item response theory to give you a rationale for choosing one item over the other in terms of the decision you want to make. Like, say you're going to give someone treatment or non-treatment depending on, you know, their level. Well, if the people are here in the middle that you're looking at, this item is a better question to ask than this item, because people below this are going to have, you know, a lower probability and a higher probability here. And in this one, you know, the probabilities are closer to each other for people above and below this level. At exactly this point, it doesn't make any difference which item you give to people. If your job is to design something, a treatment, or to ask a question of somebody at this factor level, that's okay. I mean, and similarly over here at the far right, the red item 11, you know, people at higher levels are much more likely to answer that question correctly than people who got this item, where this is only going out to say 0.6 something. Does that kind of get at your question? Or?
Yeah, I think so. I think I might have answered my own question too.
Okay.
Thank you.
Anything more? I mean, we do have classes, you know, Wes Bonifay teaches one that are entirely dedicated, you know, to item response theory. But the reason that I covered this in this class is I thought it was kind of cool that the one parameter Rouch model and the two parameter factor IRT model are exactly mathematically identical. Just saying I have a tau equivalent model in the case of a Rouch model, or I have freely estimated loadings in the case of the two parameter IRT model. And that's all those models are. They're taking things out of the printout, the factor loadings and the thresholds, and using those to make parameters they call the difficulty and the discrimination. And the reason that they do that is those two numbers tell them things about how the item is functioning as a function of the level of the latent variable. But, you know, there is absolutely no different math going on in the background here. By tradition, a lot of IRT works off of the probe at link function, but there's nothing to stop you from doing the logit function as well. And conceptually, maybe logits are a little bit nicer in clinical psychology, where you're interested in the manifest variable might be a symptom that you either have or don't have, and you're interested in knowing something about the latent variable of, say, psychopathology like depression. But, you know, in terms of the math, it's the same stuff. Well, I don't think in 3 minutes I can, work up getting into this next example, but let's kind of stop here and we'll go into a longitudinal example with a binary variable and compare the Rouch and the 2-parameter models. Okay. I will stop it here and then we can. Here's my